Hey, so today's video is a little bit different. I want to talk to you guys about a recent paper that came out. We just published this, Dynamic Amplification of Isolated Shear Walls, Insights from Layered Shell Modeling. Now, this paper is a little bit atypical for me because it's more into design or into design considerations from a modeling standpoint. So that's where I usually live in modeling and high performance computing, high fidelity modeling. And here we're looking at a design issue. And this paper is by my PhD student Patricio Palacios and my other PhD student Nicolás Mora Bowen. And my colleague Rafael Delpiano here at Universidad de los Andes, an expert in statistics. We'll see that there's a lot of statistics involved here. This was an initiative by Patricio and Nicolás, and we wanted to have a paper available to show, basically to strengthen our CVs for Patricio's scholarship that he's applying for here in Chile to continue his PhD studies. So we thought, what was a topic where we could make a little impact that was within reach, that we could do within a few months. And this is what came out, and it's actually pretty cool. So these guys are awesome. I full credit to my PhD students. They're full engineers. They're from Ecuador, and they're excellent people. And I don't know. I'm too lucky to have them. Anyway, so let's go into this paper. So here's the main idea. We're modeling buildings like this. We're not gonna go in the paper order. We're gonna be modeling structures like this, where we have shear walls, and we're gonna be looking at shear walls that look like maybe this one in the middle or this one over here, right? This is just to get a general view of what's going on. But the type of models we're gonna be doing look like this. Now, what's the research question? The research question is about dynamic amplification of isolated shear walls. Now, what is this? What you observe, or what the code observes, is that during nonlinear response of the structure, the base shear gets amplified while the base moment remains the same. And the mechanism for this is rather simple to explain. When the building is in its linear regime, its response is fundamentally controlled by its first mode response. However, when we enter nonlinear regime, then there's a higher participation of higher order modes. So the distribution of forces looks a little bit different. And the effect this has is that of lowering the resultant position or the resultant height, equivalent height of basically the lateral force. Now, this lowering of the resultant lateral force, because nonlinearity is occurs at the same time as the base moment remains the same, because you have to remember, during nonlinear response at the base is going to be yielding, and during yielding there's not much extra moment that's going to happen there. So the net effect of that is that to balance out the moment, this arrow over here, this lateral force, needs to grow. That's the basic theory. So the question is, from a design standpoint, is how much does this base shear grow, so that we can, when we specify the code, we can reinforce enough so that we ensure the type of failure that we want. Now, the way we went about this is by modeling. So we created models of just a wall, and we swept several designs. So here we can see a little table for the different models. So we varied the transverse reinforcement and the web reinforcement and the length of the walls, and we also varied how much axial load the walls were carrying. And this occurred after we validated our modeling methodology. So way down here at the end of the paper, the paper is going to be linked at the description of the video if you want to take a look at it. But we're using the advanced ASD concrete 3D material by the good people at Astea, available in OpenSeas, to model the concrete, and then hysteretic steel for the steel, of course. And so we did a pretty, and by we I mean my PhD students, of course. They're awesome. So basically, they modeled walls, shear walls, taking data from different sources, and this is the main takeaway for me, is that we're capable of modeling walls in a pretty robust fashion. So actually, the appendix of this paper for me is in the large scheme of the big scheme of things, or the big picture, is the most important thing. So we can model these hysteresis loops with these components. What else is here? You can also find the shear wall detailings that we used, and some more results. So to keep the video a little bit short, let's go back. We were modeling all these conditions, and of course we took a suite of records, mostly Chilean records, but some records from Ecuador too, and I think there's one from the US. I forget. Northridge, yeah, it's there, Northridge Parkfield, and then there's one from Ecuador. So we subjected all the models to these records, fixed base modeling, which is not my not my jive. I'm a some structure interaction guy, but here we are. We need a little paper to help us out. And then what we discovered is that we can look at a lot of results. So what's this that we have here? The maximum drift versus the amplification. Now the amplification is defined by the nonlinear shear force normalized by the linear shear force times the overstrength ratio. So that's pretty standard. And so the main thing is the code. The code tells you that the dynamic amplification of shear is controlled by the number of stories. So we have a little section here at the beginning. I'm going back and forth in this paper. I'm sorry if this is getting you dizzy. But here in the code provisions for shear amplification, we have the ACI 318, 19, and 25, the definitions for this amplification. So these are all based on geometric considerations. So what's the story height of the building and all of this stuff. But when we take a look at basically how the number of stories correlate with the amplification and the max drift, we see basically nothing. So there's nothing there. And then if we actually take a look here and we color so this is the same plot as before, but now the color is not the number of stories, but is the amount of axial force. We see some patterns starting to emerge. We see some things, these dots doing some things. For example, you can see at 0.3, at large axial loads, the amplification seems to be capped, whereas at lower or more normal values, there seems to be no such limit. So the big takeaway at the end of the paper, I won't stress you with all the details, but the big picture here is maybe this plot can help. This plot can help. So here we have the amplification factor, and here is a little metric that tells you the equivalent or the normalized position of the resultant force. So remember, way back at the tippy top, I explained that the amplification comes from the fact that the resultant force has to come down as the moment that the base remains the same, and that means it needs to get amplified. So what we're doing here is actually using this reduction in height, the normalized reduction in height of the resultant force, defined as the ratio between the base moment and the base shear, as a proxy to how much amplification we can get. And actually we get pretty good results if we take a look at this versus the number of story. Of course, the number of stories is garbage as a predictor. So basically here's the number of stories, and here is it looks like the same picture. Or is it this one, the one that I want to take a look at? No, this is the one, and you can see that you get kind of a reasonable spread of the points when you take a look at that. So basically, that is a much better predictor of the amplification than just the code required the story height or the number of stories. And here we have a little model that we came up. This is the statistics part of the paper. where we basically do a fit at different percentiles for the data. So data mean, this would be the mean model, but then you have, if you want to fit at the 95th or the 99th percentile, you can also have models. So different, this would be different like safety levels if you're doing a code. So this is this is not my jive. I'm not totally comfortable with the implications of this, but I'm really happy to have these PhD students that I have. I'm really grateful for them, and to see what they are capable of doing with the stuff that's available over here. We ran a lot of cases. Each of these points is a full non-linear analysis that takes a lot of hours. There's a lot of data. There's a lot of looking at stuff. Many tools were developed to visualize, to make sense of this, and I'm really happy about this. It also it also goes to show you the state of Chilean PhD, uh, the PhD scene, where it's become so competitive down here that we actually need to have papers before you get elected to do a PhD over here. There's a lot of people coming in. The Chilean scholarship is very good. So the basically the competence is or the competition is very high. Yeah, so that's the origin of that paper. So if it seems strange to you that me, a dude that's into modeling and soul structure interaction, is getting into design, this is the reason. See you guys next time.